The concept of even and odd. Is 0 even, odd, or neither? The answer is that 0 is an even integer. Remember, an integer is even when it leaves remainder 0 when divided by 2. 0 leaves remainder 0 when divided by any integer. 0 is a multiple of all the integers. 0 is very much an even number. Let's start from the basics. Classification of numbers. Real numbers. GMAT does not deal in complex numbers, so all the numbers that appear on the GMAT are always real numbers. Real numbers can be classified into two types: irrational numbers, numbers that cannot be represented in P over Q form, where P and Q are integers. Rational numbers, numbers that can be represented in P over Q form, where P and Q are integers. And of course, Q is not equal to 0. The examples are given here. These are the examples of irrational numbers, and these are all the examples of rational numbers. Remember, even an integer is a rational number because something like 2 can be represented by 2 over 1. Now, rational numbers. How can rational numbers be divided into two types? Fractions and integers. How can integers be divided into two types? There are many ways. One is even or odd. The other way is prime or non-prime. Prime numbers are numbers which have exactly two factors. Let's look at some of the exceptions, some of the interesting observations. Remember, 0 is an even number, as we just saw. 2 is the only prime number that is even, and 1 is not prime because a prime number is supposed to have two factors. 1 has only one factor. Be aware of these exceptions. Very often, questions on GMAT test these particular rules, and in such questions, these observations end up forming exceptions to the general cases. Let's delve deeper into the concept of even and odd. The concept is even times even is even. Even times odd is even. Odd times odd is odd. Even plus even is even. Even plus odd is odd. Odd plus odd is even. Even to the power of even is even. Even to the power odd is even. Odd to the power even is odd. And odd to the power odd is also odd. A very basic concept, but some beautiful questions can be made on it. Let's warm up with some examples here. If P, Q, and R are positive integers, and the product P times Q times R divided by 8 is an integer, which of the following must be even? Now remember, must-be cases are those where you do not get a no even once. So the right approach in these questions is to try to get a no. The moment you get a no, you have an answer. Okay, please note, this is not one question with 5 answer choices. These are 6 different questions, and the answer to each can be yes as well as no. One possibility is that only one of them is even. Something like this: P equals 8, Q equals 3, R equals 5. The other possibility is that 2 of them are even integers. Say P equals 4, Q equals 2, and R equals, say, 3. The other possibility is that all 3 of them are even integers. Something like this. Now let's play around. P plus Q plus R. We have to look for just one case where no is a possibility. So yes, P plus Q plus R is even. In this case, you can see 2 are even, 1 is odd, and therefore we can say that yes, there are cases where P plus Q plus R can be odd. Hence, no. In this case, P plus Q plus R must not be even. P times Q plus R, once again, see in this case, P times Q would be even, plus R is odd. So again, we have a case. So we can use a no for this one as well. Use a no or a cross mark, whatever is intuitively easier for you. In case of this sum, a case where only one of them is even, see this case, P times Q would be even, P times R would be even, but Q times R would be odd. Overall, even plus even would be odd. So we can say no for this choice as well. For PQ divided by R, there will be a lot of cases where PQ divided by R will not be an integer on the first place. Something like this. See, PQ divided by R is a fraction, so of course, it won't be an integer in such cases, leave alone being an even integer. So here also, we can say that no, this is not even in all the cases. Next case. p raised to the power q raised to the power r. In cases where p is odd, for example if p equals 1, q equals 8, r equals 3, in cases such as these, you will see that p times q times r divided by 8 is an integer. But the value of this expression is odd, so even this will not suffice. Next case, p times q raised to the power of r. In combinations where p is odd, q is odd, and r is even, see pqr divided by 8 would be an integer, but p times q raised to the power r would still be odd and not even. So there is none of the 6 cases where the expression must be even. One key aspect that data sufficiency teaches you is to be open to all possibilities. So see 6 cases, but in none of the 6 cases, we can say that the value of the expression is definitely even, given this case to be true. In case you did not get all 6 correct, you have one more chance. In this, you will see that the condition that p times q times r divided by 8 is met, but figure out that pqr is even. So the base is definitely even. Now one may think that even to the power of odd is also even, and even raised to the power even is also even. However, there are cases such as p equals 1, q equals 1, r equals 8, where you will figure out that pqr would be 1 times 1 times 8 raised to the power p plus q minus r. 1 plus 1 minus 8 is negative 6. Hence, you will have 8 raised to the power of negative 6, which would be a fraction and therefore not an even integer. So even in this case, there are values which satisfy pqr divided by 8 being an integer, but the value of the expression not being even. So even this does not work. We have 7 cross marks. This was a must-be question. Now let's solve a similar maybe question. The same set. You may want to pause the video and solve it yourself. Remember, maybe questions are those where if the condition is met even once, then you select that answer choice as correct. So once again, the possibilities are even, 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 or even, odd, odd, or even, odd. All the 3 possibilities are there, and of course, p, q, r can each be in any order here. p plus q plus r. This would be true in this case as well as this case. So this is possible. Maybe, yes. pq plus r. This would also be true in an even times even plus even, or even times odd plus even case. So this is also possible. This would also be possible when all 3 are even, or when 2 are even. So yes, pq divided by r would be even in cases such as this. p equals 8, q equals 2, r equals 1. So of course, in many cases, this would be possible. Next, p raised to the power q raised to the power r. Of course, it would be possible in cases such as 2 to the power 2 to the power 2. Many such cases are possible. p times q raised to the power r. So again, 2 times 2 raised to the power 2 kind of cases would lead to even values. Even this one, when p equals q equals r equals 2, this would be even. So in case of maybe, each of the 7 may be even, and we have 7 check marks here. Some GMAT-like practice questions now. 3 data sufficiency questions. Please pause the video and try solving these yourself. In case you are able to get all 3 questions right, you have really understood the concept. The question is x even? Now, see, 8y is supposed to be even, irrespective of whether y is even or odd. Then the sum is odd. 8y has to be even. Sum is odd. Therefore, 5x has to be odd. If 5x is odd, x is odd. X is odd, so we have an answer. That no, x is not even. Remember, no can also be an answer. Statement 1 is sufficient. Statement 2 doesn't talk about x at all, and therefore statement 2 cannot be sufficient. 1 is sufficient, 2 is not. A is the right answer. Look at the second question here. 5x plus 7y is odd. That means either the first term is even and the second term is odd, or the first term is odd and the second term is even. But definitely one term is even and the other is odd. we cannot be sure whether x is even or odd. Not sufficient. Look at statement 2. 6x is going to be even, irrespective of whether x is even or odd. This is even. 5y can be even or odd, but if the sum is even, then 6x plus 5y is even suggests that 5y should also be even. Even plus only even can be even. So this gives us some good information, that 5y is even, and therefore y is even. But this doesn't tell us much about x, so even this is not sufficient. On combining, what do we get? On combining, we know that 5y is even, therefore y is even, and therefore 7y is going to be even. If 7y is even, 5x has to be odd, and therefore x is odd. So on combining, we get no, x is not even, x is odd. Remember, no can also be an answer. Combining help, and therefore C is the correct answer choice. You could have also done this question a different way. Add the two. You get 11x plus 12y. That is, when you are combining, 11x plus 12y is odd plus even, which is odd. Now 12y is bound to be even, and therefore 11x must be odd. If 11x is odd, x is odd. So on combining, we say that x is odd, and therefore we get no as an answer. Look at the last one here. 7x plus 9y is even, and therefore either both are even or both are odd. 10x is bound to be even. The sum is odd, and therefore y must be odd. So 1 did not work. 2 did not work because 10x would be even, irrespective of whether x is even or odd. On combining, what do we get? Combining, we know that y is odd, and therefore it is the second case that both are odd. So on combining, we know that x is odd, and therefore combining did give us a unique, consistent answer. The right answer is C. Once again, you could have solved this question a different way. On combining, you could have added the two. 7x plus 10x is 17x, plus 9y plus 15y is 24y, which is even plus odd, and therefore odd. 24y is bound to be even. The sum is odd. Therefore, 17x is odd. If 17x is odd, x must be odd. So that's another way to reach the right answer. The correct set of answers here is A, C, C. If you got all three correct, good job. Last digit. One of the GMAT's most favorite concept. Try solving this one. Did you get 7 as the answer? Did you get to that in like 30 seconds? If not, don't worry. Just follow this video. The underlying concept across all the last digit questions is that for finding the last digit, you need not multiply the complete numbers. Just multiply the digits on the units place. For example, 112 times 113. If I were to figure out the digit on the units place of this product, I need not multiply and figure out that the value of this product is, very quickly, 12,656. For the last digit, we can simply multiply 2 and 3 and get a 6. 12 times 13, the value is 156, but we could get a 6 straight away by just multiplying 2 and 3. Similarly, 2 times 3. Of course, the last digit is going to be 6. So see, as long as the last digits are 2 and 3, the product has a 6 on the units place. With this learning, let's apply the concept on a few questions. Here is a really complex expression. Of course, multiplying this will take forever. However, you don't have to multiply. Concept is that take the last digits of all the numbers and multiply them. So we just catch hold of all the last digits, 3, 6, 2 onwards. See, 3, 6, 2, and now, while multiplying, just hold on to the last digit. 3 times 6 is 18, so 8 is important. 8 times 2 equals 16, so 6 is important. 6 times 3 equals 18, so 8 is important. 8 times 9 equals 72, so 2 is important. 2 times 5 equals 10, so 0. 0 times 7 would be 0. The trick here is that you could have spotted 2 and 5 in these expressions earlier, 2 and 5 or 6 and 5, and you could figure out that 2 times 5 or 6 times 5 leads to a 0, and therefore the result is going to have a 0 at the units place. Try these questions. Please pause the video and try solving these yourself. 3 questions here. Find the last digit. So very quickly, 4. 4 times 7 equals 28, so 8. 8 times 6 equals 48, so 8. 8 times 3 equals 24, so 4. 4 times 2 equals 8. 8 times 8 equals 64. So the answer is 4. Now 8, 6, 4, 6, 2, 6. The answer is 6. 7, 8, 6, 2, 4. The answer is 4. The next concept is last 2 digits. To find the last 2 digits of such a big number, the underlying concept is that to find the last 2 digits, one needs to multiply the last 2 digits of all the terms. Since multiplying all the 2-digit numbers will be cumbersome, you will always find a catch. The catch in this question is the friendly numbers 20 and 25. So see, if you multiply 25 and 20 first, we get a double zero at the end, and then double zero multiplied by all the other last 2 digits, 87, 79, 47, 77, would be double zero only. So the answer is going to be double zero in this one. Find the last 2 digits of this one now. So what friendly numbers do you see? 42 and 15. So spot 42 and 15. Multiply these first. You get 630, and once you have got 1 0 here, you know that the last digit is going to be 0. 42 has been taken. 15 has been taken. You have a 0 at the end, so these 2 removed, and only 3 remains. So now, if we find out the last digit of all the remaining terms, we will effectively get the second last digit. So 9. 9 times 7 equals 63, so 3. 3 times 1 equals 3, so 3. 3 times 9 equals 27. And don't forget this 3. 27 means 7, so 7 times 3, which is 21. We have 1 as the answer here. Okay, so 10. Or the way I did it here, I caught hold of 3 here. 3 times 9 equals 27, and then 7, 1, 9 together. So this is 27 times 63. The penultimate digit turns out to be 1, and we had 0 as the last digit anyway. So the last 2 digits are 10. Try some questions. Please pause the video and try solving these yourself. There are 3 questions here. In this one, we see friendly numbers as 75 and 08. Their product is 600. So that gives you double zero, and therefore, no matter what the other terms are, the last 2 digits are going to be double zero only. What are the friendly numbers here? 25 and 06. Their product is 150. That means 50 at the end. 50 means 0 would be the last digit, and 5 multiplied by all the other terms being odd. The last 2 digits are going to be 5 and 0. Look at this one. You already have a 0 here. So take the 0 out. Remove the 0 and now find the last digit of whatever is left. 7. 7 times 3 equals 21. So 1. 1 times 7 equals 7. 7 times 3 equals 21. So 1. And 1 times 4 equals 4. 0 was anyway at the end. So the last 2 digits are 40. One of the GMAT's favorite question types. This one. Find the last digit of something like this, 38 raised to the power 175. Concept is that step 1, consider only the last digit of the base. So if 38 is here, you would by now understand that this 3 is not going to play any role. It's only 8 that decides what is going to be on the units place. So consider the last digit, say b. Step 2 is to find the remainder when the power is divided by 4. Let's call this r. Always 4. So if the power is 175, we divide 175 by 4 and find the remainder. Step 3 is to simply take b raised to the power r. Okay, b raised to the power r. These are the 3 steps. Tip: to find the remainder of a number when it is divided by 4, simply divide the last 2 digits by 4. So let's apply this concept on this question here. 38 raised to the power 175. Step 1 is that base is 8. Step 2 is to find the remainder of the power with 4. So remainder of 175 with 4 which is going to be the same as the remainder of 75 with 4. Because 75 is the last two digits, the remainder is 3 here. Step 3 is quite simply 8 raised to the power 3, which is 512. And therefore, the last digit is 2. The answer is going to be 2 here. Let's take another example. 537 raised to the power 3,958. Pause the video, solve it yourself. Step 1. The base is 7, the last digit here. Step 2. Divide the power with 4, 3958 with 4 to get the remainder, or simply divide the last two digits, 58 with 4, to get the remainder, which is 2 here. Step 3 is easy. Simply 7 raised to the power 2, which is 49, and therefore the answer is 9. An exception to this is, whenever the remainder is 0, take the remainder as 4. For example, 32 raised to the power 1240. So see, if we had taken the remainder of 40 with 4, that turns out to be 0. And 2 to the power 0 would be 1. Now 32 is an even number. Even raised to the power of any positive integer. The value would always be even. So the last digit can never be 1 here. As suggested, in all these cases, whenever you get the remainder as 0, don't take it as 0. Take it as 4. So step 1, the base is 2. Step 2 is we divide the power with 4, 1240 with 4, or simply the last two digits, 40 with 4. Either way, we get 0 as the remainder. And whenever we get 0, we have to take 4. So we don't take 2 to the power of 0, we take 2 to the power of 4, which is 16. The last digit is 6, and therefore the answer is 6 here. One more example. 518 raised to the power of 780. Step 1. Base is 8. Step 2. Find the remainder of the power with 4. 780 with 4, or simply 80 with 4. We get remainder 0. So we don't take 0, we take 4. And therefore the answer is going to be 8 to the power of 4. You don't have to find the entire value of 8 to the power of 4. You can simply do an 8 to the power of 2 times 8 to the power of 2 equals 64 times 64. The answer turns out to be 6. One set of practice questions. Please pause the video and try solving these yourself. Practically, this turns out to be 8 to the power of 3, which is 2. So the answer is 2 here. Practically, this turns out to be 3 to the power of 3. So the answer is 7 here. This turns out to be 6 to the power of 2 plus 4 to the power of 4. 6 to the power of 2 would lead to a units place of 6. Plus 4 to the power of 4 would lead to a units place of 6. 6 plus 6 is 12, and therefore the answer is 2. 9 to the power of 3 minus 2 to the power of 4, which leads to 9 minus 6. The answer is 3. A final question now. Look at this one. What do we get? Practically, 7 to the power of 3 minus 2 to the power of 4. This turns out to be 3. 7 to the power of 3 is 343, so 3. Minus 2 to the power of 4 is 16, so 6. 3 minus 6 turns out to be negative 3. What do we do now? Do we just remove the negative sign? That won't be correct. Imagine the last digit here is 3. The last digit here is 6, and you are subtracting. What do we do? In such cases, you always borrow from the penultimate digit, and this 3 becomes 13. It's 13 minus 6, which is 7. So whenever you get something negative, always add 10 to it. The answer is not 3. The answer is negative 3 plus 10, which is 7. That's the right answer. What is the number of factors of 2 to the power of 10 times 5 to the power of 10? Did you get 121? Did you get that in like 20 seconds? If not, don't worry. Just concentrate on this video. Let's start from basics. Factors and multiples. What is the difference? Factors of a number are integers which can divide the given number. Multiples of a number are integers which are divisible by the given number. For example, 20. Factors are going to be 1, 2, 4, 5, 10, 20. Multiples are going to be 20, 40, 60, onwards, infinite. Factors of a number are always finite, while the multiples are always infinite. Underlying concept for finding the number of factors. What is the number of factors of 240? So if you were to do this manually, it would take a lot of time. 1, 2, 3, 4, 5, 6, 8, 10, 12, and many more. There is a possibility that you will end up missing some factors. So there has to be a smarter way out. The concept is, first of all, break the number into its prime factors. So factorize the number into prime numbers. 240. How you can do it quickly is first remove the 0. 0 can be replaced by 2 times 5. Then 24 is 2 to the power of 3 times 3 to the power of 1. So it opens into 2 to the power of 4 times 3 to the power of 1 times 5 to the power of 1. Step 2 is to add 1 to each power and then multiply all the terms. Why add 1? Try to understand what is going on here. We have 2's, we have 3's, and we have 5's. If 1, 2, 1, 3, 1, 5 are taken and multiplied, some number would be formed, which would be a factor of 240. If 2 2's, 1, 3, 1, 5 are taken and multiplied, they would lead to a different factor of 240. So it's about figuring out what is the number of combinations of selecting among 4 2's, 1, 3, and 1, 5. 4 2's can be selected in how many ways? 1, 2, 2 2's, 3 2's, 4 2's, and there's a fifth case also of no 2's at all. So 4 2's can be selected in 5 ways. 1 3 can be selected in 2 ways. 1 3 or no 3. 1 5 can be selected in 2 ways. 1 5 or no 5. That is why 1 is added to each power. So 5 times 2 times 2, which is 20. And therefore 240 has 20 factors. Try these questions. Please pause the video and solve these yourself. 1500 can be broken into 5 times 3 times 5 to the power of 2 times 2 to the power of 2. They combine together to form 5 to the power of 3 times 3 to the power of 1 times 2 to the power of 2. Now add 1 to every power and multiply. 3 becomes 4. 3 raised to the power 1. So 2 raised to the power 2, so 3. The number of factors is 4 times 2 times 3 equals 24. Remember, one step is very important here, which is to combine the powers 5 times 5 to the power of 2. It is important to combine it to form 5 to the power of 3. If I had not combined, imagine the powers would have been 1, 1, 2, 2, and I would have multiplied 2, 2, 3, 3, and I would have got a bigger answer, 36, which is not the right answer. The right answer is lower than that, 24. So always combine the bases, and of course make sure that every base is a prime number. 720. Let's break 720. We get 2 to the power of 4 times 3 to the power of 2 times 5 to the power of 1. We just need to add 1 to the powers and multiply. So it becomes 5 times 3 times 2. The number of factors is 30. In the third case, the bases are already prime. You just need to add 1 to the powers and multiply. So 5 times 6 times 4 times 2 times 5 turns out to be 1200. In the last case, you have to break the numbers into prime bases. This is what it simplifies to. Remember to combine the same prime bases for adding the powers. It simplifies to 2 to the power of 9 times 3 to the power of 5 times 5 to the power of 4. Add 1 to the powers, we get 10, 6, 5. The number of factors is 300. Some DS practice questions. Please pause the video and try these. Look at the first one. Statement 1 says, x equals p to the power of 2 times q. P and q have no common factors other than 1. While they do not have any common factors, they may themselves be big numbers. For example, p can be 2 to the power of 10. Q can be 3 to the power of 10. See, mutually, p and q don't have any prime factors common, but they can have other big factors. Therefore, statement 1 is not sufficient. It leads to way too many possibilities. Look at statement 2. It says that p and q are prime numbers, but the question is about x. Statement 2 doesn't talk about x. This can never be sufficient. Let's combine. On combining, we know that p and q are prime numbers. They have no common factors. That means they are different prime numbers. Therefore, x is of the form prime 1 to the power of 2 times prime 2 to the power of 1. Number of factors it is going to have is 2 plus 1 times 1 plus 1, which is 3 times 2. It's going to have 6 factors. So, on combining, we could reach a unique answer. Combining worked, and therefore C is the right answer. Let's look at the second question now. X equals P times Q. P and Q have exactly one common prime factor. So, only one factor is common, but still, they could be huge numbers. For example, P can be 2 times 5 to the power of 10, and Q can be 2 times 3 to the power of 10. See, there is only one common prime factor, but there are many other factors as well. Hence, various possibilities exist. Statement 1 is not going to be sufficient. Statement 2 doesn't talk about x, so this is not going to be sufficient. On combining, we get that P and Q each have exactly 3 factors. When can a number have 3 factors? The only case is when it is square of a prime number. Imagine, that's the only case. 2 plus 1. The number will have 3 factors. Otherwise, a number can never have 3 factors. So statement 2 is suggesting that P as well as Q is square of a prime number, and statement 1 is suggesting that P and Q have exactly one common prime factor. That means prime 1 and prime 2 are the same prime number. Hence, P equals Q equals square of the same prime number. Therefore, x is equal to some prime number, whatever that number is. It doesn't matter. Raised to the power 4. X equals prime to the power 4. Therefore, x is going to have 4 plus 1 equals 5 factors. On combining, we could reach a unique answer. 5. Combining worked. So the correct answer is C. 2 more DS questions. Please pause the video and solve these. P and Q have no common factor other than 1, but P and Q may be big numbers. For example, P can be 2 to the power of 10. Q can be 3 to the power of 10. Therefore, x can have lots of factors. Statement 1 leads to numerous possibilities and is thus not sufficient. Statement 2 doesn't talk about x. So this cannot be sufficient. Let's combine and see. In simple words, statement 2 is saying that P equals A times B, Q equals C times D, where A, B, C, D are all different prime numbers. Therefore, on combining, we can say that x equals A to the power of 2 times B to the power of 2 times C times D, where A, B, C, D are all different prime numbers. Therefore, number of factors that x is going to have is 3 times 3 times 2 times 2. Whatever the answer is, 36, that's not important. The point is that, on combining, we are able to reach a unique answer. Combining worked. C is the right answer. Look at the last one here. This is the best of the lot. Please take a moment to solve this one. X equals P times Q. P and Q have exactly one common prime factor. But P and Q may have other factors as well. For example, P can be something like 5 times 2 to the power of 10. Q can be something like 5 times 3 to the power of 10. See, P and Q have exactly one common prime factor, which is 5, but have lots of other factors. So statement 1 does not lead to a unique answer. It should be eliminated. Look at statement 2 now. P and Q have exactly 3 factors. X equals P times Q. Now imagine x equals P times Q. P and Q have exactly 3 factors. When is that possible? When they are square of a prime number. So x equals square of a prime number times square of another prime number. Now the catch is that the 2 prime numbers may be the same or they may be different. Therefore, many students will feel the need for combining the 2 statements to figure that out. And yes, when you combine, you know that they happen to be square of the same prime number. Therefore, it is x is something like prime to the power of 4. Therefore, x has 5 factors. So C is a very popular answer choice for this question. Many students choose C, but that's not the right answer. Look at statement 2 a bit more carefully. Yes, we know that there are 2 possibilities for x is prime to the power of 2 times prime to the power of 2. But the question is not asking the number of factors of x. We don't have to reach to 5, the value. We have to answer whether the number of factors is 6. Now imagine if they are different prime numbers, x will have 3 times 3 equals 9 factors. If they are the same prime number, x is going to be prime to the power of 4, and therefore x will have 5 factors. So x can have 9 factors or 5 factors. In either case, it is not going to have 6 factors. Therefore, statement 2 alone leads to a consistent no as answer. Statement 2 is sufficient, and therefore the answer is not C. The answer is B. If you got this answer right and through the right logic, by applying all the possibilities, you have done a very fine job. A session on factorials. As usual, I have a question for you here. Did you get 1? Did you get that in like 30 seconds? If not, don't worry. Just concentrate on this video. The basic concept. N factorial equals n times n minus 1 times n minus 2 times n minus 3 times until 1. Beautiful questions can be made on this simple concept. The first one. What is the highest prime factor of 500 factorial? You have to work 500 backwards. 500 is of course not prime. Then 499. To find whether a number is prime, take the square root, find an approximate value. It's 22 point something, so round it off on the lower side. 22 point something, so 22. Now from 2 to 22, look for all the prime numbers. If the number is not divisible by any prime number in this range, it is going to be a prime number. So let's see. 2, of course, is not a factor of 499. 3, no. 5, no. 7, no. 11, no. 13, no. 17, no. 19, no. That's all. So that means 499 is a prime number. The largest prime number that is a factor of 500, the answer is 499. The next one here. The last non-zero digit in the expansion of 12 factorial. 12 factorial expands into 12 times 11 times 10, 9, 8, 7, and then 6 factorial is 720. Let's get rid of all the zeros first because it's about the last non-zero digit. And then, if you remember it from the last digit session, to find the last digit, catch hold of all the last digits involved and keep on multiplying. So 2 times 1 equals 2, 2 times 9 equals 18, hold 8, 8 times 8 equals 64, hold 4, 4 times 7 equals 28, hold 8, 8 times 2 equals 16. So the answer is 6. That's the right answer. Once again, quickly, 2, 2, 2, 8, 4, 8, 6. The value is 6. Next, what is the remainder when 15 factorial plus 100 is divided by 13? Imagine 15 factorial plus 100 being divided by 13. If you remember from the remainders video, you can find the respective remainders and then apply the operator in between, the plus sign here. 15 factorial is of course a multiple of 13. So this part is going to leave 0 remainder. Look at 100. 91 is a multiple of 13, so 100 will leave remainder 9. Overall, remainder is 0 plus 9. The answer is 9. Now let's look at GMAT's favorite concept. A very, very important concept, this one. If 6 to the power of x is a factor of 40 factorial, what is the highest possible integer value of x? Now, very often students come up with obvious answers, such as 6 or 2. These are not the correct answer. The right answer is much higher in value. Here are the steps. Look for the highest prime number in the divisor. Count the number of times this prime number appears in the factorial. So if you are finding the highest power of 6 in 40 factorial, it's not about 6 so much. It is about 6 being 2 times 3. Imagine when you expand 40 factorial. A number such as 8 will come. A number such as 27 will come in the expansion of 40 factorial. And when they are multiplied, you see, 8 is not a multiple of 6. 27 is not a multiple of 6, but 8 times 27 is 216, which is same as 6 cubed. So see, suddenly we have 3 powers of 6 out of these numbers, which did not have a 6 in them. So it's not about the complete base. It is always about the highest prime factor of the base. So 6 equals 3 times 2. Of course, the number of 2's will be more, number of 3's will be fewer. Always count the highest power of the highest prime factor of the divisor. So it's about the number of 3's here. 40 factorial, 1 to 40, when expanded, will have 13 numbers, which are multiple of 3. So 3, 6, 9, until 39. There are 13 such numbers, but then many of them, such as 9, 18, 27, these are going to have more than one 3 in them. Therefore, figure out the number of such numbers which have a higher power of 3. So 40 divided by 3 to the power of 2, or 40 divided by 9. There are 4 such numbers which will have 2 3's in them. Then, there will be one number, 27, which has a 3 cube, or 3 3's in it. Now imagine there are 13 numbers which have 1 3 each. There are 4 numbers which have 2 3's each. One 3 got counted here, and the second 3 gets counted here. Then there is one number that has 3 3's in it. 1 3 got counted here, 1 3 got counted here, and the third 3 gets counted here. Therefore, the answer is, quite simply, 13 plus 4 plus 1. The answer is 18. If you think this was lengthy, don't worry. A lot of it was just to explain the logic. Practically, the question can be solved very quickly. For example, if we have to find the highest power of, let us say, 15 in 100 factorial, how do we do it? First of all, we know 15 is 5 times 3. The higher prime number is 5, and therefore 5 will occur less often. Imagine when 100 factorial is expanded. Until 100, one has to move only 3 places to get a multiple of 3. But one has to move 5 places to get a multiple of 5. Therefore, 5 decides what is going to be the highest power of 15. Now, how many 5's in 100 factorial? 100 divided by 5 is 20. And then, rather than finding a 100 divided by 5 to the power of 2 or 100 divided by 25, we can simply find a 20 divided by 5, which is 4. This can be no longer divided by 5. So the answer is 20 plus 4, 24. That's how you can do it really quickly. Try these questions. Please pause the video and solve these. 7 in 50 factorial. So 50 divided by 7 is 7. Remember, keep leaving the fractional part. Next, 7 divided by 7 is 1 more. Overall, 7 plus 1. The answer is 8. Next, 5 in 50 factorial. 50 divided by 5 is 10. Then 10 divided by 5 is 2 more. Overall, 10 plus 2. The answer is 12. 11 in 150 factorial. 150 divided by 11 is 13. 13 divided by 11 will be 1 more. Overall, 13 plus 1. The answer is 14. Next, 70 is the divisor here. 70 means 2 times 5 times 7. The highest prime factor is 7 here. So consider 7. 50 divided by 7 is 7, and 7 divided by 7 is 1 more. Overall, 7 plus 1 equals 8. The answer is same as this. See, the highest power of 7 is 8, and the highest power of 70 is also 8. This is because the highest prime factor of 70 as well as is the same 7. Next, 15 in 50 factorial. 15 is 5 times 3, so it's about 5 here. 50 divided by 5 equals 10. 10 divided by 5 equals 2. Overall, 10 plus 2 equals 12. Next, 9. This is interesting. It's about finding the pair of 3's. So 50 divided by 3 is 16. 16 divided by 3 is 5. 5 divided by 3 is 1. This adds up to 22, but 22 is not the correct answer. It's about 9. 9 means 3 square. So to get 9, we need a pair of 3's. So the answer is not 22. The answer is 22 divided by 2, which is 11. 11 is the correct answer. Next, 16. Once again, 50 divided by 2 is 25. 25 divided by 2 is 12. Of course, I neglect the fractional parts every time. 12 divided by 2 is 6. 6 divided by 2 is 3. 3 divided by 2 is 1. Added up, we get 47. However, 47 is not the correct answer. 47 is the highest power of 2. For 16, we need groups of 4 2's. How many such groups are possible? The answer is 47 divided by 4. Always ignore the fractional part. The answer is 11. That's our answer. Next, 63. Now 63 is 3 times 3 times 7. One may argue that 2 3s will occur later. 1 7 will occur sooner. You can always judge it. See 1 times 2 times 3, 4, 5, 6, 7, until 50. So to get 1 7, one has to travel 7 places. To get 2 3s, 1 3 comes here, second 3 comes here. So to get a pair of 3s, one has to travel only 6 places. So it is 7 that decides the answer. So 50 divided by 7 is 7, and 7 divided by 7 means 1 more. 7 plus 1. The answer is 8. Now, in case you are confused about which factor to choose, I would suggest that find answer using both the values and then choose an answer that is smaller. For example, in this case, if you were confused, try to get answer using 3 as well. 50 divided by 3 is 16. 16 divided by 3 is 5. 5 divided by 3 is 1. The sum turns out to be 22. And then pairs of 3s. So 22 divided by 2, the value is 11. Therefore, if I choose 3 as the deciding factor, or pair of 3s as the deciding factor, I get 11 as the answer. If I choose 7 as the deciding factor, I get 8 as the answer. Remember, always the smaller value wins. So the answer would be 8 and not 11. So whenever confused, find multiple answers and choose the smallest value. Next, some DS practice questions for practice. Please pause the video and solve these. Highest power of 9 has to be determined. If the highest power of 3 is 41, the highest power of 9 is going to be 41 divided by 2. Always ignore the fractional part. So highest power, if 9, is going to be 20. We get a unique answer, 20. Statement 1 is very much sufficient. Look at statement 2 now. Highest power of 6 also means the highest power of 3 times 2. 2 doesn't matter. If highest power of 6 is 41, the highest power of 3 is 41. So we know the highest power of 3, the highest power of 9, would be once again 41 divided by 2, which is 20. So statement 2 also leads to a unique answer, 20. 1 is sufficient, 2 is sufficient. D is the right answer. Look at the second question here. Highest power of 9 is 9. This is a tricky one. So this means that the highest power of 3 squared is 9. Number of 3s could be, imagine, 18, but it could be 19 as well. See, we just saw 41 divided by 2 for 20. The number of 3s here is not 40, it is 41, one more. So if there are 9 9s, there could be 18 3s, or there could be 19 3s. 2 cases are possible. We don't have a unique answer. So statement 1 is not sufficient. Statement 2 is, of course, sufficient because it says the highest power of 6 is 19. 6 means 3 times 2. If the highest power of 6 is 19, the highest power of 3 is also 19. Statement 2 is sufficient. 1 is not sufficient. 2 is sufficient. B is the right answer. A session on terminating and reoccurring fractions. Do you think this fraction, 127 divided by 120, is going to terminate? The answer is no. If it took you too long to figure out, don't worry, just wait for 5 minutes. Terminating fractions to begin with. Which of the following will terminate? A standard GMAT question. The concept is that a fraction would terminate if its denominator has no prime factors other than 2 or 5. Imagine 1 divided by 2 is 0.5. This terminates. 1 divided by 5 is 0.2. This also terminates. Imagine any other prime number in the denominator. It will never terminate. 1 divided by 3 equals 0.33. 1 divided by 7 equals 0.142857. None of these terminate. And even these numbers, 1 divided by 2 is terminating, but if I multiply the denominator with another prime number, see now this will no longer terminate. This will reoccur. 1 divided by 5 is terminating. 1 divided by 35. This will no longer terminate. So the concept is very simple. A fraction would terminate if its denominator has only 2's and 5's as the factors. So in this case, 3 divided by 7 has a 7, so this will not terminate. 27 has 3, so this will not terminate. 48 has a lot of 2's, but it also has a 3. so this will also not terminate. 160 has only 2's and 5's, so this is going to terminate. This is the right answer. 143 has 11 as well as 13. This will not terminate. So choice D with denominator 160 is only such denominator. D is the right answer choice. Which of the following will terminate? Look at this one. Please pause the video, solve it yourself. Now you will realize that each denominator has some or the other prime factor other than 2 and 5. Therefore, there must be a catch in the numerators. 140 has a 7. 7 cannot be cancelled. 280 has a 7, but C63 also has a 7. Therefore, D can be simplified to 9 divided by 40, and now this will terminate. You don't have to find the value, 0.225. You just know that the denominator 40 has only 2's and 5's as factors, and therefore this particular fraction is going to terminate. D is the right answer choice. Reoccurring fractions. Which of the following fractions, when expanded, will lead to a decimal value that reoccurs most late? These are the answer choices. The concept is, once again, very simple. The fraction with the largest prime factor in the denominator will reoccur most late. In A, the largest prime factor is 13. In B, it is 17. In C, the denominator is 140. So the highest prime factor is 7. In D, again, it is 7. In E, it is 3. B has the highest prime factor in the denominator, 17, and therefore option B represents a fraction that will reoccur most late. Among the given answer choices, B is the right answer choice. Some practice questions. Please pause the video and solve these yourself. 170 has a 17. This is not going to terminate. 480 has 3. This is not going to terminate. 1400 has a 7. This will not terminate. 640 has only 2's and 5's as prime factors, so this is going to terminate. 450 has a 3. This is not going to terminate. D is the right answer choice. Look at this one. The highest prime factor in option A, the denominator, is 7. In the case of choice B, the denominator is 130. The highest prime factor is 13. In C, the highest prime factor is 37. In D, the highest prime factor in the denominator is 17. In choice E, the highest prime factor in the denominator is 11. 37 is the highest among all, and therefore option C is the correct answer choice. Some DS questions. Please pause the video and solve these yourself. Will the fraction p divided by q terminate? We know it's about the denominator. 16 is a factor of q, so if q is something like, let's say, 16 itself or 32, q has only 2's as factors, and the answer would be yes. This will terminate. For such values, the answer would be yes. However, when q is something like 48, see, 16 is very much a factor of 48, but in such a case, the fraction will not terminate. Yes and no, both are possible. So statement 1 is not sufficient. 400 is a multiple of q, so that means q times some other integer, say k, equals 400. 400 has only 2's and 5's as prime factors. So q, as well as k, cannot be multiples of any prime numbers other than 2's and 5's, and in such a case, p divided by q will definitely terminate. Second is sufficient. Statement 1 is not sufficient. 2 is sufficient. The answer is option B. Look at this question now. 7 is a factor of q. We cannot be sure about no because q has a 7 in it, but maybe p also has a 7 in it. So yes and no, both are possible. Statement 1 is not sufficient. Look at statement 2. This alone is of course not sufficient because it talks about the numerator and not the denominator. On combining, this is very interesting. Many students will get this wrong. See, in the denominator, we have 7. In the numerator, we know that we have something which is not a multiple of 14, but imagine it can still be a multiple of 7. For example, if it is something like 21 divided by 70, imagine this is going to terminate. So in this case, the answer would be yes. For a different value, such as 20 divided by 70, the answer would be no. So see, even on combining, we have cases where yes as well as no is possible. So even combining did not lead to a unique answer, and therefore E is the right answer choice. As usual, I have a question for you here. I hope you got 1 as the answer. In case you did not, don't worry. By the end of this video, you will be able to solve all such questions with great ease. So we are on remainders, and this is type 1. Let's start from the basics. What if we have to find the remainder when such a huge term is divided by a number, say 4 in this case? The underlying concept is that you don't have to actually multiply the entire term and then find the remainder. You can rather find the remainder of each respective term here with 4, and thereafter multiply the respective remainders. Let's practically apply this concept. In this given question, this is a huge expression. We need not multiply and then divide. We can first divide and then multiply. To find the remainder with 4, we just need to divide the last 2 digits by 4. So 327, the remainder with 4 would be the same when 27 is divided by 4. That's 3. 45 would leave remainder 1. 59 would leave 3. Similarly, each term would leave some respective remainder. Now see, such a huge expression would reduce to a very simple expression. And once again, we don't have to actually multiply the entire term. We can divide this into 2 parts. We say this is 9, this is 18. So it's about remainder of 9 times 18 with 4. 9 would leave remainder 1 with 4. 18 would give remainder 2 when divided by 4. The answer to this question is 2. In light of this learning, please try solving these questions. With divisor 25 also, we need to look at the last 2 digits only. So 26 with 25 will leave remainder 1. This would practically leave 2. This would leave 2. This would leave 3. This would leave 4. So overall, it is 1 times 2 times 2 times 3 times 4, which is 48. Now 48 with divisor 25 would leave remainder 23. Look at the next one. With 7, there is no simple rule of finding the remainder. So you have to practically divide. But then trust the question maker. The numbers would be friendly. 420 is a multiple of 7, so 427 would be multiple of 7, and therefore 428 will leave remainder 1 with 7. This would leave 2. This would leave 3. This would leave 1. This would leave 3. Overall, it is about finding remainder of 1 times 2 times 3 times 1 times 3 with 7. So practically, it is about remainder of 18 with 7. The answer is 4. Look at this one. It's 2, 3, 1, 4. Overall, the product is 24. 24 with divisor 13 will leave 11 remainder. The divisor is 3. To find the remainder with 3, you must add all the digits of a number and divide this sum by 3. This is an easy way of finding remainders with 3 as well as 9. The sum is 16 here. So when divided by 3, the remainder would be 1. Had the divisor been 9, the remainder would have been 7 because the sum is 16. 16 would leave remainder 7 with 9. So that's how you find remainders quickly with 3 and 9. The sum is 16, so 1 again. The sum is 25, so 1 again. Sum is 17, so remainder 2 here. Sum is 16, so 1. Product of these remainders is 2, so the answer is 2. The 4 answers here are 23, 4, 11, and 2. I hope you got all the 4 questions correct. Now let's move to slightly more complex questions. Look at this. This is the question we had on the first slide. How do we solve this? First step should be to combine the bases. See, the powers are the same, so we can write it as 10 to the power of 99 to the power of 99. Now, rather than actually multiplying the powers, we know that it has to be 10 times 10 times 10 many, many times. It's 9,801 times, but that's not important. The point is, it's 10 times 10 times 10, and each time 10 is divided by 9. The remainder is 1. So practically, the remainder is 1 times 1 times 1 lots of times, and therefore the overall remainder is 1, because 1, no matter how many times it is multiplied with itself, the product remains 1. In light of this approach, let's look at a slightly more complicated question. The base is the same, but now the divisor is 11. So the same concept. 10 raised to some power, and now it's being divided by 11. The concept is that always try to get a positive 1 or negative 1 as remainder. So 10, if you look at it closely, the remainder of 10 with 11 is 10, but in other sense, the remainder can also be called negative 1, because 10 is 1 less than 11. So this is what it is. No matter how many times, it doesn't matter. The point is that every time 10 is divided by 11, we can say that the remainder is negative 1. Now, see negative 1, where there are 2 terms, it becomes positive. When there are 3 terms, it becomes negative. So for even terms, the product is plus 1. For odd terms, the product is negative 1. 99 times 99 is something odd. Therefore, we get negative 1 times negative 1 multiplied odd number of times, leading to negative 1 as the product. Now, remainder has to be something positive. So whenever you find the remainder as something negative, always add the divisor to it. So negative 1 plus 11. The answer is 10 here. We are on remainders type 2. As usual, I have a question for you here. Try solving it. Did you get 6 as the answer? Did you get that in less than 1 minute? If no, don't worry. By the end of this video, you will be able to do so. Let's start from the basics. A number leaves remainder 93 when divided by 120. What remainder will it leave when divided by 40? This is a favorite GMAT question type. The underlying concept is that for a number x to leave remainder r with divisor d, the number should be of the form d times p plus r, where p is a positive integer. So for this question, the number x has to be 120 times some positive integer plus 93. That is why, imagine this part is leaving remainder 0 and this part is leaving remainder 93 when divided by 120. And that is why, effectively, x is leaving remainder 93 when divided by 120. Now what we require is the remainder of this term with 40. 120p plus 93 is the number. We are dividing this by 40. 120p will leave remainder 0, and 93 will leave remainder 13 when divided by 40. The sign in between these two terms is of addition. So practically, the remainder turns out to be 0 plus 13 equals 13. That's the right answer. In light of this concept, let's try a few questions. Please solve these questions. A number leaves a remainder 87 when divided by 150. What remainder will it leave when divided by each of the following values? Please pause the video and try solving these yourself. 7 questions here. The number is leaving remainder 87 when divided by 150. So the number has to be something like 150k plus 87, where k is a positive integer. Now with 50, 150k will leave remainder 0. 87 will leave remainder 37 with 50. Hence, the answer is 37. With 30, 150k will leave remainder 0. 87 will leave 27. So the answer is 27. With 25, 150k will leave remainder 0. 87 will leave 12. So the answer is 12. With 15, 150k will leave remainder 0. 87 will leave 12. So the answer is 12. With 6, 150k will leave 0. 87 will leave 3. So the answer is 3. With 300. Now this is interesting. See, 150k can leave multiple remainders with 300. See closely, 300 is not a factor of 150. 300 is a multiple of 150. In the earlier cases, it was easy because all these numbers were factors of 150, and the remainder was 0 every time. With 300, there are 2 different cases. The remainder shall be 150 when k is odd, and the remainder shall be 0 when k is even. So this part can leave remainder 0 as well as 150. There are 2 possible answers. the answer is going to be 87, or 87 plus 150 equals 237. Similarly, with 450, there are three possibilities. 150k can leave remainder 150 when k is of the form 3n plus 1. 150k can leave remainder 300 when k is of the form 3n plus 2, and it can leave remainder 0 when k is a multiple of 3, and therefore of the form 3n. So this part can leave three different remainders, and therefore the remainder with 450 can be 87, 237, or 387. Three different answers are possible. In light of this learning, attempt this question now. Please pause the video and solve it yourself. All right, I am solving it now. It's of the form 11k plus 2. When this number, 11k plus 2, is divided by 44, there are four different answers possible. When k is of the form 4n, and therefore k is a multiple of 4, we will have this part giving 0 remainder. So practically, the remainder would be 0 plus 2, which is 2. When k is of the form 4n plus 1, this part will give remainder 11, and this will continue to give remainder 2. So the overall remainder will be 11 plus 2 equals 13. For example, put n equals 5 here. 11 times 5 plus 2 equals 57. 57 gives remainder 13 with 44. When k is of the 4n plus 2 form, for example, put n equals 6. You will have 11 times 6 plus 2 equals 68, leading to a remainder of 24 with 44. The fourth case is when k is of 4n plus 3 form. For example, when n equals 7 here, 11 times 7 plus 2 equals 79. 79 gives remainder 35 with 44. After this again, you will get the remainder 2. So there are four different cases, because 11 times 1, 11 times 2, 11 times 3, 11 times 4. Each of the four cases lead to different values of the remainder. The possible remainders are 2, 13, 24, and 35. Out of these, only 13 matches. So out of the given choices, 13 is the only possible remainder. And therefore, the answer is option B. Here is a next practice question. Please pause the video and solve it yourself. This is the same question that we had on the first slide. X leaves remainder 17 with 24. So x has to be of the form 24k plus 17, where k is a positive integer. 6x becomes 6 times 24k plus 17 equals 144k plus 102. Now 6x has to be divided by 48, and the remainder has to be determined. 144k will leave remainder 0 with 48, and 102 will leave remainder 6 with 48. Therefore, overall, the remainder is 0 plus 6 equals 6. That is the right answer. Now, we have 3 DS questions. Please pause the video and solve these yourself. The first one here. The number is leaving remainder 100 with 144. So it has to be of the form 144k plus 100. When we divide this by 72, this part is going to leave remainder 0, and this part is going to leave remainder 28. So overall, 28 is going to be the remainder. Statement 1 is sufficient. In this case, the number is going to be something like 36p plus 20. 36p can leave two remainders with 72, 36 and 0. Therefore, a unique answer is not going to be possible. Statement 2 is not sufficient. 1 is sufficient, 2 is not. A is the right answer choice. Look at the next one. It is of the form 3x plus 30 equals 120p plus 93. By dividing the complete equation by 3, we can simplify this to x equals 40p plus 21. Now, when divided by 40, this part is going to give remainder 0, and this part is going to give remainder 21. So statement 1 is going to be sufficient. Let's look at the second statement. 5x minus 10 leaves remainder 15 when divided by 20. 20 is a factor of 40. It's not a multiple of 40. See, 120 worked because 120 is a multiple of 40. 20 is further smaller than 40, and now we have 5 here. So the equation turns out to be 5x minus 10 equals 20k plus 15. When we divide the entire equation by 5, we are going to have something like x minus 2 equals 4k plus 3. So of course this is not going to be sufficient. There are going to be 10 different answers for this one. A statement is sufficient only when it leads you to one unique answer. So statement 2 is not sufficient. Once again, the answer is A here. Look at this one. Statement 1 says x is of the form 40p plus 15. So 40 and 60. Nothing unique can be said about the remainder. This expression will lead to multiple remainders, with 60. So not sufficient. Statement 1 is not sufficient. Statement 2 says x equals 30q plus 15. Again, there are two different possibilities. 30q may leave remainder 30 or 0 with 60. So this is also not going to be sufficient. On combining, if a number is leaving remainder 15, the same remainder with 40 as well as 30, then it means the number is going to leave same remainder with the LCM, the least common multiple of 40 and 30. The LCM of 40 and 30 is 120. Hence, we can say that x is of the form 120k plus 15. Now 120k will leave remainder 0 with 60. Therefore, practically, the remainder is going to be 15. So on combining, we could get to a unique answer, 15. Combining worked, and therefore C is the correct answer. I hope you got the right combination of A, and C for these three questions. We are on remainders, and this is type 3. As always, I have a question for you here. Did you get 8 as the answer? Did you get it in less than a minute? If not, don't worry. Just wait for this video to get over. So, a very interesting type, this one. What is the remainder when such a number, some base raised to the power, some power, is divided by a divisor? Let's say 7 is the divisor in this case. The concept is that look for higher powers of the base to get a remainder of positive 1 or negative 1 with the divisor. So see, 2 is the base and 7 is the divisor. The distance is 5. It's neither positive 1 nor negative 1. 2 squared would be 4. Now the distance is 3. Still, it is not positive 1 or negative 1. Then 2 cubed is 8. See, 8 is 7 plus 1. We got a desired positive 1 difference here. So if we convert the base 2 into a base 8, we will start getting a remainder of positive 1 with the divisor 7. Let's apply this. In this question, we have to find the remainder of 2 to the power of 300 with 7. We express it as 8 to the power of 100 divided by 7. Why 8? Because 8 leaves remainder 1 with 7. Now, this can be written in the following way. 8 times 8 times 8, 100 times, divided by 7. Now, each 8 leaves remainder 1 with 7. So we can say that the remainder is going to be 1 times 1 times 1, 100 times. Therefore, practically, the remainder is going to be 1. That is the answer to this question, 1. Let's take one more example. Let's say remainder of 2 to the power of 303 with 9. In this case, you see we get 2 cubed is 8, and 8 gives negative 1 remainder with 9. We write this as 8 to the power of 101 with 9. This is practically 8 times 8 times 8, 101 times, or negative 1 times negative 1 times negative 1, 101 times. Because every 8 gives a remainder of negative 1 with 9. Then, this is being multiplied odd number of times. Negative 1 times negative 1, 101 times, odd number times. Therefore, effectively, this product is going to be negative 1. An important concept here. Whenever you get the remainder as something negative, add divisor to it. This is something I have covered in one of the earlier videos. So the remainder is negative 1 plus 9. The answer is 8. In light of this concept, let us now try some practice questions. Please pause the video and try solving these yourself. So, 3 squared is 9. That gives us remainder 1 with 8. So we can write this as 9 to the power of 25. We need to find the remainder with 8. Each 9 will give remainder 1 with 8. Hence, it is practically 1 to the power of 25, and therefore the answer is 1. The next case, 92 to the power of 60, and we need remainder with 15. 92, the base, is greater than 15, the divisor. So first of all, divide the base, 92, by 15 and reduce it. This becomes 2 to the power of 60, because 92 leaves remainder 2 with 15. Now let's try higher powers of 2. We can see 2 to the power of 4 leaves a remainder of positive 1, because 2 to the power of 4 is 16, which is 15 plus 1. Therefore, the fourth power of 2 is going to help. So we write 2 to the power of 60 as 60 to the power of 15. Now, when we divide this by 15, it is practically 1 to the power of 15. Therefore, the answer is 1 again. Please don't think that the answer is going to be always 1. Very often, of course, you will have other answers, probably in the next question. So first of all, reduce the base. 70 divided by 17 gives remainder 2. So once again, it becomes 2 to the power of 60. Again, 17. So 16 is going to help because 16 will give a remainder of negative 1. So the expression becomes 16 to the power of 15. And we need to find the remainder with 17. Practically, this means negative 1 to the power of 15, which is negative 1. Remember, whenever you have the remainder as something negative, you must add the divisor to it. So practically, the answer is going to be negative 1 plus 17 equals 16. Look at the next question. First step, divide the base 100 by 7. You get remainder 2. So the expression becomes 2 to the power of 100. 2 cubed is going to help because 2 cubed is 8, which is 7 plus 1. So we write this as 2 cubed to the power of 33 times 2 to the power of 1. See, this is power 99, and this is power 1. So overall, the power is 100. 2 cubed is 8, which leaves remainder 1. So the remainder is, practically, 1 to the power of 33 times 2 to the power of 1. Therefore, the remainder is 2. The answer is 2 here. Next, 2 to the power of 60. And we need remainder with 15. That's an easy question. We just solved this. It is the same as this question. The answer is going to be the same. We write this as 16 to the power of 15. The remainder with 15 turns out to be 1 to the power of 15. Therefore, the answer is 1. If you got all the 5 questions correct, you have done a very good job. One more question on the same concept. First of all, you combine the base to get 10 to the power of 99 to the power of 99. Now, this is like saying 10 times 10 times 10 lots of times. Each 10 will leave remainder 1 with 9. So it's 1 times 1 times 1 many times. Again, this 9,801 times is not important. The point is that it's going to be 10 times 10 lots of times. And every time 10 is divided by 9, the remainder is 1. Therefore, practically, the answer is 1. We are on remainders, and this is type 4. A very interesting type, this one. Look at the question here. Did you get the answer 9? Did you get that in 20 seconds or fewer? If not, don't worry. Just concentrate on this video. Let's look at another question on the same lines. What is the remainder when this huge term is divided by 32? The underlying concept is that to find the remainder when the divisor is 2 to the power of n or 5 to the power of n, divide the last n digits by 2 to the power of n or 5 to the power of n respectively. And why so? See, we all know that if a huge term such as this has to be divided by 4, we always take the last 2 digits. But why? Because 87687,300 plus 21 is how this number can be written. Now, this part, because it has a double zero at the end, it is going to be a multiple of 100. If it is a multiple of 100, it is going to be a multiple of 4 as well. That is why, for a remainder with 4, we look at just the last 2 digits. This concept can be applied on many other divisors as well. For example, if you are to find the remainder with 20, the same concept can apply, because see, you have a double zero at the end. So for a remainder with 20, also we can just look at the last 2 digits. For 25 also, we can look at just the last 2 digits, because this part is a multiple of 100, so it is also a multiple of 25. For 50 also, we can look at just the last 2 digits. Similarly, we can say that if we are to find the remainder with 8, we can just look at the last 3 digits. We can write it this way. That's 321, 3 zeros at the end. Every 0 means 2 times 5. Therefore, if we are to find the remainder with 8, we can just find the remainder for the last 3 digits, 321 here, and we will get the same answer. Similarly, if we are to find the remainder of this entire term with 125, we can just find the remainder of the last 3 digits with 125, and the answer would be the same. So this is how this concept works. For 2 to the power of n, or 5 to the power of n, consider the last n digits. Now it is 32 here. 32 is 2 to the power of 5. So consider the last 5 digits, 20,197. Remainder of 20,197 with 32. You can solve this easily in a few seconds. However, if you spot a 3 here, I can take the last 6 digits also. Of course, the remainder is going to be the same. Now see, 320 can be cancelled. 197 remains. This is easier to solve. The answer is going to be 5. Even if you had strictly taken the last 5 digits, it would take a bit longer, but you would get the same result, 5. So the answer to this question is 5. Please pause the video and solve these questions. 16 means 2 to the power of 4. So the last 4 digits become important. 0197. When divided by 16, 192 goes. 5 remains. The answer is 5. 125 means 5 cubed. So the last 3 digits matter. 197, when divided by 125, the remainder is 72. 64 is 2 to the power of 6. So the last 6 digits matter. 640,197 divided by 64. This much goes easily. That's 10 times. 197. 192 goes, and 5 remains. The answer is 5. 625 is 5 to the power of 4. So the last 4 digits matter. 0197 divided by 625. The dividend is smaller than the divisor. Therefore, the dividend, 197 itself, becomes the remainder. So these are the 4 answers. Let's practice some more. Please pause the video and try solving these yourself. 8 is 2 cubed. So the last 3 digits, 312 divided by 8, the remainder is 0. 16 is 2 to the power of 4. So we need to divide the last 4 digits by 16. Remainder of 2,312 with 16. The remainder is 8. 25 is 5 squared. So divide just the last 2 digits by 25. The remainder is 12. 50 is a factor of 100. Hence, we need to consider just the last 2 digits. The answer is 12. 200 is a factor of 1,000. Therefore, we need to consider the last 3 digits. So remainder of 312 with 200. The answer is 112. 250 is again a factor of 1,000. Therefore, last 3 digits need to be considered. The answer would be the remainder of 312 with 250. The answer is 62. Lastly, 500, again, is a factor of 1,000. Therefore, last 3 digits matter, and it's going to be the remainder of 312 with 500. The answer is 312. I hope you got all the 7 questions right. We are on remainders, and this is type 5. As always, I have a question for you here. Did you get 153? Did you get that in less than 1 minute? If not, please attempt this once again after watching the complete video. We have split this type into 2 subtypes, type 5.1 and 5.2. Let's look at 5.1 first. The question is on these lines. Find the smallest number other than 2 which leaves a remainder of 2 when divided by 6, 8, or 10. The underlying concept is that for determining a number that leaves the same remainder with different divisors, find the LCM, which is least common multiple of the different divisors, and add the common remainder to it. So, if a number is leaving remainder 2 with 6, 8, as well as 10, it is fine to say that the number, let's say x, is a sum of 2 numbers, some number here plus 2, a number here that leaves remainder 0 with 6, 8, as well as 10. Which is such smallest number? The smallest such number is 0. Of course, 0 plus 2 is 2. That is why the question says other than 2. After 0, the smallest such number is the LCM of 6, 8, and 10. And that is why this concept that you have to find the LCM of the different divisors and then add common remainder to the LCM. Okay, so the LCM is 120. Therefore, the required number is 120 plus 2 equals 122. In case you have forgotten how to find LCM, here is a quick primer. There are many ways to figure it out. The one I would suggest is to break the numbers into prime bases. For example, 24, 60, 50. We first break the numbers into the prime bases. Here we are. Then we select the prime numbers with their respective highest powers and multiply them all. So the highest power of 2 here is 3. The highest power of 3 here is 1. And the highest power of 5 here is 2. So the LCM is 2 cubed times 3 to the power of 1 times 5 squared. The value is 600. So, for example, if you had a question, find the smallest number other than 15 that leaves a remainder of 15 when divided by 24, 60, or 50, we just found the LCM, it is 600. We simply need to add the common remainder, which is 15, to it. The answer to this question would be 615. So that was type 5.1. Let's move to type 5.2. Question is on these lines. Find the smallest number that leaves remainders 3, 5, and 9 when divided by 8, 10, and 14 respectively. The concept in such cases, you find that the difference between each divisor and its respective remainder is a constant. You have 8, 10, and 14, and the respective remainders are 3, 5, and 9. See, the common difference is 5 here every time. So if x is the desired number, if we add 5, the common difference, then each of these remainders will become greater by 5. And see, practically, each of these remainders will become equal to 0. Therefore, on adding the common difference, 5, to the required number, I am getting a number that is a multiple of each of the divisors, 8, 10, as well as 14. Therefore, on adding the common difference, I am getting the LCM. Hence, the concept is that whenever you find that the difference between the divisors and the respective remainders is a constant, you must take the LCM and subtract the common difference from it. The common difference here is 5, and the LCM is 280. Therefore, the desired answer is 280 minus 5 equals 275. The answer is 275. Let us now practice some questions. Please pause the video and try solving these yourself. The numbers are 10, 14, 18, and 20. The common difference you will see is 9. Every time. 10 minus 1 is 9. 14 minus 5 is 9. 18 minus 9 is 9. 20 minus 11 is 9. So we need the value of LCM minus 9. LCM here is 1260. So we subtract the common difference, 9, from it, and the answer we get is 1260 minus 9 equals 1251. Try doing this yourself. 1000 plus x leaves a remainder 2 when divided by 3, 5, or 6. So 1000 plus x has to be of this form. There has to be a part which is a multiple of 3, 5, as well as 6, so that this part leaves a remainder 0 with 3, 5, or 6. And then we add 2 to it. Okay, so the number here has to be a multiple of 3, 5, and 6. The LCM of 3, 5, and 6 is 30. The number here has to be a multiple of 30. So 30k plus 2 is what we are looking at. K is a positive integer, and the value of this has to be just a bit greater than 1000. So see, 30 times 34 will take it just above 1000. This value is 1020 plus 2 equals 1022. So 1000 plus x equals 1022. Therefore, the value of x is 22. That is the answer. Look at this one. It's a DS question. X leaves the same remainder when divided by 8, 10, and y. We have to figure out what is the remainder when x is divided by 8. So we know it's going to be some same remainder, but we don't know what that same remainder is. Therefore, statement 1 is, of course, not sufficient. Many students will think that statement 2 is not sufficient, but no, that's not correct. This is a very interesting question. We know that x has to be less than the LCM of 8, 10, and y. So this part, there is some number here, which is the LCM of 8, 10, and y. No matter what the value of y is, when x is divided by 8, we can say that we have to divide this number by 8 and this number by 8. Now this number, whatever it is, no matter what y is, this is going to be a multiple of 8, and if it is a multiple of 8, this part is going to give 0 remainder. This is, of course, going to give -5 remainder. So the number we are looking at, whatever the value of x, the remainder is going to be 0 minus 5. It is going to be -5. Then you know that whenever the remainder turns out to be something negative, we add the divisor to it. So we add 8 to -5, and we get that the remainder is 3. And see, we got to this value, 3, using statement 2 alone. 1 is not sufficient. 2 is sufficient. Therefore, B is the correct answer choice. We are on remainders, and this is type 6. Look at the question here. Could you solve this in less than 30 seconds? If not, don't worry. Just follow me. The concept involved is n factorial is a multiple of all integers from 1 to n. Hence, if you have to find the remainder of this expression with 7, we can easily figure out that 20 factorial is going to be a multiple of 7. 20 factorial is going to leave remainder 0 when divided by 7. Therefore, the remainder is confined to this part, 43. 43, when divided by 7, the remainder is 1. Therefore, practically, the remainder is 1. That is the concept, and very interesting questions can be made on this concept. Let's practice a few questions. 3 questions here. Please pause the video. Solve these yourself. Now, 25 factorial is going to have a 20 in it, and 100 leaves remainder 0 with 20. So the answer is going to be 0 plus 0 equals 0 here. Now 50, one may think that 50 is greater than 25, but 50 is actually 2 times 5 times 5. And when 25 factorial is expanded, of course, there will be many 2's and 5's. Therefore, 25 factorial is a multiple of 50. Therefore, this part is going to leave remainder 0. 100 is also going to leave a remainder 0 when divided by 50, and therefore the answer is again 0. Now 200. So while 200 is greater than 25, 200 can be broken into 2 square times 5 square. Of course, when 25 factorial is expanded, there are going to be lots of 2's and lots of 5's. Therefore, 200 is a factor of 25 factorial. Thus, this part is going to leave remainder 0 when divided by 200, and 100 when divided by 200 is going to leave remainder 100. Overall, the remainder is 0 plus 100. The answer is 100. Therefore, the 3 answers here are 0, 0, and 100. Look at this one. Try solving it yourself. 40 factorial. So with 3, this is going to leave remainder 0. With 91, this is going to leave remainder 1, and therefore 3 is not a factor of 40 factorial plus 91. Or in other words, 40 factorial plus 91 is not a multiple of 3. 7, of course. This is a multiple of 7. 91 is also a multiple of 7. Therefore, yes, 40 factorial plus 91 is a multiple of 7. Look at 13. 40 factorial is, of course, a multiple of 13. 91 is a multiple of 13. Therefore, the sum is going to be a multiple of 13. The right answer choice is 2 and 3 only. The next topic, LCM and HCF. Look at this question. When can LCM and HCF of a set of numbers be the same? They can be the same only when all the terms in the set are equal. Let's start from the basics. LCM, or least common multiple, for a set of numbers is the smallest number that is divisible by each number in the set. Finding LCM. There are many ways. The one I would recommend is this one. Break all the numbers into the prime bases. For example, 24, 60, 50. Break each number into the prime forms. Thereafter, choose the highest power for each of the prime base. So the highest power for 2 is 3, the highest power of 3 is 1, and the highest power of 5 is 2. So the LCM is going to be the product of these 3 terms. 600 is the LCM for 24, 60, 50. Highest common factor, or HCF for a set of integers, is the highest integer that divides each number in the set. So for 24, 48, 60, and 84, the highest common factor is 12, as 12 is the highest integer that divides each of them. How to find the highest common factor? Again, break all the terms into the prime bases, and then choose the prime numbers with highest power that is common to all the terms. Let's take an example, the same example. We first break them into prime bases. And now we see that the highest power of 2 that is common everywhere is 2. Highest power of 3 that is common everywhere is 1. Highest power of 5 that is common everywhere is 0. Highest power of 7 that is common everywhere is also 0. So 2, 1, 0, 0, highest common factor is going to be 2 squared times 3 to the power of 1 times 5 to the power of 0 times 7 to the power of 0. The value is 12. Let's practice a few questions based on this concept of highest common factor and least common multiple. Look at this one. 2 questions based on this information stem. Please pause the video, try solving it yourself. The first one, maximum number of coins that each child may have got. So 24 coins, 36 coins, 40 coins, and 60 coins. They have to be distributed in such a way that no coin is left. All the coins have to be distributed. And the condition is that each child must get equal number of coins, and each child can get coins from only one of the 4 friends involved. Quite clearly, for the coins to get exhausted, the number of coins that each friend must give must divide each of these 4 values. In simple words, the highest such number would be the highest common factor of 24, 36, 40, and 60, which is 4. 4 is the highest integer that divides each of these 4 integers. Look at the next part of the question. For minimum number of children, we need to maximize the number of coins per child. So we need to take this case only, where each friend is giving coins in bunches of 4. Therefore, the first friend would give it to 6, the second will give it to 9, the third will give it to 10, and the fourth friend will give it to 15 children. So the answer is 6 plus 9 plus 10 plus 15 equals 40. Another way of solving it can be to add all the terms. 24 plus 36 plus 40 plus 60 equals 160, and divide 160 by the maximum number of coins per child. Either way, you get 40 as the answer. So the right pair of answers here is 4 and 40. Look at these questions. Data sufficiency. Please pause the video. Try solving these yourself. Highest common factor of x, y, and z. Now, one may argue that statement 1 has only x and y. There is no z in it. So how can this be sufficient? The fact is that this statement is sufficient because for x and y, the HCF is 1. So no matter what z is, the HCF of x, y, and z is going to be 1 only. So statement 1 is sufficient. It leads us to conclude that the highest common factor of x, y, and z is 1. Similarly, statement 2, y and z have nothing in common. See 81 and 49. There is no factor other than 1 common. Therefore, the highest common factor of y and z is 1. So no matter what x is, the highest common factor of the 3 terms is going to be 1 again. So 1 was sufficient. 2 is sufficient. The answer is D. Let's look at the next question now. HCF of 4 integers, a, b, c, and d. Now, a and b have a 60 in common. Now, c and d may or may not have 60 or some factor of 60 in common. So statement 1 is not sufficient. B and c have a 3 in common. So if a and d each have a 3 as well, then the highest common factor would be 3. Otherwise, the highest common factor would be 1. So statement 2 is also not sufficient. On combining, see A, B, and C have 3 in common. Now if D also has 3 as a factor, the HCF of the 4 terms would be 3. Otherwise, the HCF would be 1. So on combining, 2 answers are still possible, 3 and 1. We are still not able to get to a unique answer. Therefore, statements 1 and 2 together are also not sufficient. E is the correct answer. Surds and indices, also referred to as roots and exponents. As always, I have a question for you here. Is your answer yes? If so, that's not correct because when x equals 1, y can be anything. That's an easy one to catch. Basic principles. A to the power of m times a to the power of n. The powers get added. This case is different. Here the powers get multiplied. In the case of division, the powers get subtracted. And 1 divided by a to the power of m equals a to the power of negative m. All basic stuff. Let's get down to learning by examples. This is a common GMAT question, generally a low difficulty question. To solve this question, you have to find the value of x. The concept involved is, in such questions, convert the bases on the right-hand side as well as left-hand side into the basic prime number involved. In this case, the prime number involved is 3. So we convert 27 into 3 cubed, 9 into 3 square, and 81 into 3 to the power of 4. We do that, and then the rest is easy arithmetic. You can solve it for the value x. On solving, x turns out to be 9 divided by 4, or 2.25. That's an easy question. The second question, the second type, is something like this. Now in these questions, the concept is that whenever you see very high powers involved, you will almost always see a big surd being taken common and getting cancelled. So in this case, 2 to the power of 99 can be taken common in numerator as well as denominator. Now this big term can be cancelled. What you get, the rest, is something very small. It simplifies to 2. Do this yourself. Take 3 to the power of 199 common in numerator as well as denominator. These big terms get cancelled, and what's left is something easy to calculate. 93 divided by 91 is the answer here. A couple of DS practice questions. Try solving these two yourself. You have to find the value of p minus q. P to the power of q equals 121. So there are 3 possible cases: 11 squared, negative 11 squared, and 121 to the power of 1. Remember, DS is a lot about considering all possibilities. So in case you missed any of these 3 cases, you may have got this question wrong. P and Q are integers, but there are 3 possibilities, and therefore there are 3 different possible values of P minus Q. Statement 1 is not sufficient. P to the power of Q is 121. P times Q is not 121. So this case can be eliminated. Still, there are 2 cases left, and therefore statement 2 is also not sufficient. On combining, still these 2 cases remain, and therefore, even on combining, a unique answer is not possible. The answer is option E. Look at this one. P to the power of Q is 121, and P and Q are positive integers. So there are only 2 possibilities: 11 squared and 121 to the power of 1. Still, we don't have a unique value. Therefore, statement 1 is not sufficient. Statement 2 says that Q is a prime number. 2 possible cases are 11 squared and negative 11 squared, and there are numerous other cases, such as cube root of 121 to the power of 3. It only says that Q is a prime number. It doesn't say anything about P. So of course there are various possible cases. Statement 2 is not sufficient. On combining, what do we get? Statement 1 led to these 2 possible cases, and Statement 2 says that Q is a prime number. Therefore, this case can be eliminated. 1 is not a prime number. So on combining, we are left with only 1 case, 11 squared. The value of P minus Q can be determined. So combining worked. The right answer is C. The right pair of answers here is E and C.